Hello there. Today we are doing derivatives day 2, and this is probably my last video lesson to you. So last lesson I alluded to doing derivatives with limits, and so today we're going to do that and also just basically also explain to you what's called the power rule. So I have this picture here, and you don't have to take notes or anything right now. Just watch and listen. I have a few demonstrations, and then when we start doing examples, you can take notes and stuff. But anyway, let's say you have a curve, and you saw last time how we wanted to get the slope of the curve, basically the derivative, and this is how you do it. So this is a definition limit-wise. So if you're going to do the derivative by taking the limit. We're going to start with that today. So anyway, I have this point x right here. So you would notice that if I travel up x, then over here is f of x, right? So basically, maybe it's the point, 5, 4, all right? So what you're going to do, or what people do to explain this, they're going to travel a distance, and that distance is going to be either called delta x, or in our definition, it's going to be called h. So we're going to call it h. That space right there is h. So this spot right here would be called x plus h because it's over x plus h. And so if I go up here to there, and so I'm just going to estimate it's about at 9 or something. But anyway, this would be my function's value at x plus h. So x plus h is just some random amount, right? H is just a random amount. So what we can do is if I want to think of a line between these 2 points. So you would call that a secant line, because a secant line is a line that goes through 2 points of a curve. Tangent line is when it's just through 1 point. So if I did the slope of that blue line, remember the slope is y2 minus y1 over x2 minus x1. So I'm going to do that for here. So my second point is this one right here. So my y value is f of x plus h minus f of x, because that's my y value for the first point, over my x value for the second point is this guy, so x plus h minus the first one, x. So if I clean that up, the slope of my secant line is going to be f of x plus h, we don't know what that is, minus f of x. But on the bottom here, on the denominator, do you see how these x's cancel out? So I just have h. So this is the slope of my secant line. So that secant line, what we're going to do, what I'm going to show you in the next few pages, what's going to happen is that h value is going to get smaller and smaller and smaller. So this h value is going to go closer to x. So that means at this point is going to come further down the curve, and your secant line is going to change. It's going to maybe be like that. Always going through this point right here, but it changes along the curve. And then maybe the secant line gets even closer. So then the secant line, maybe it's through this point and this one. So it gets closer and closer and closer. And what it does, as h gets smaller and smaller and smaller, what happens is that secant line basically approaches the actual tangent line. And the tangent line is what you really want. That tangent line right there. All right, it's not perfect, but that's what you really want. And so what we're going to do is we're going to say that h goes towards 0, all right, because we want h to get smaller. And so what we end up doing is we take this little statement right here, this slope, we say the limit as h goes to 0 of the slope of the secant line. So f of x plus h minus f of x over h. And that right there is the limit definition of a derivative. And so, because remember the derivative is the slope of a tangent line, and this is getting us the slope of the tangent line. So I just have a couple more things to kind of reiterate this. So I'm going to go to this site right now. Let's see. So anyway, I just wanted to show you here some pictures of what I was doing. So like a secant line, and again, you're moving this point right here, so it comes closer and closer and closer to the actual spot. And right there, then you get your tangent line. So h is getting smaller and smaller and smaller. All right. So same thing on this one right here, and it just has some little equations on the side. They don't change or anything, but again, this is moving, and it turns a corner and goes towards the actual tangent line. So right here, this one's kind of cool because you can see the h value changing in the middle. So notice when I drag this red dot, oops, I can't drag it. Maybe I drag this one. Yeah, when I drag the green one to the left, h is getting smaller, and notice how the secant line is approaching the actual tangent line. So that's what we mean by h getting smaller and smaller and smaller until it's actually 0. And when it's 0, the secant line and the tangent line match each other. And so over here in blue, you see the definition I was just going over with you. And so, I don't know, I thought that was kind of cool just to see it in movement. Anyway, so this is also another kind of picture of what's going on. You can see here that first of all, your secant line is really long, then it gets shorter and shorter until finally it's exactly what you want. So the slope of your secant line is f of x plus h minus f of x over, remember it was x plus h minus h, I'm sorry, x plus h minus x, and then the x's went away. So the slope of the tangent line is what we're going for, and that is the limit as h goes to 0 of this expression, f of x plus h minus f of x over h. Okay, and you notice we can't plug in 0 right now because that would make the bottom 0, so you had to do some fixing before you can do that. All right, so let's get to the notes. So you should start taking notes now, and this will be the beginning. So this is Intro to Calculus, and we are on derivatives, day 2. All right, so first of all, we have the limit definition of a derivative. And also, this is also called first principles. It's like the limit by first principles. Sometimes you see those words too. But that's interchangeable. All right, so here it is. We have the limit as h goes to 0, fraction. I have f of x plus h minus f of x over h. All right, and you last time in your homework you had to work out some of these and work out this expression, but this is our main point right here. And this is kind of like the long way to do derivatives until we discover the short way in a minute. Anyway, so we're going to use this, here's our first example. We're going to use this definition to do a couple derivatives. And these derivatives, this first one at least, you're going to know the answer because it's going to be a line. So I want to use the limit definition of a derivative to find f prime of x. So remember, f prime of x means a derivative. And so here is my f of x. So f of x is 4x plus 2. So, it's a line, so the slope is always 4. So you know that the answer is going to come out to 4 here. So it should be no big shocker when we get that, but let me show you how to do the limit definition. So we're going to need two things. We need one thing, basically. We need f of x plus h, and we also need f of x, which we already have right here. So f of x plus h will be 4x plus h plus 2. All right, so let me do it. So I have limit as h goes to 0. I'm going to put f of x plus h. Now I can work that out. It's going to be 4x plus 4h plus 2 minus f of x. Now when we minus f of x, remember that minus is going to everything in there. So it's going to be minus 4x, and then the 2 is going to turn into a minus 2 as well, all over h. All right, so let's do some canceling. So that goes away, the 2's go away. And so what I'm left with is my limit as h goes to 0 of 4h over h. And then the h's cancel. So what I'm left with is the limit as h goes to 0 of 4. And the limit of 4, as you learned last time, is just 4. And so when you go to MathSpace and work this out, it's going to want to show like some work in between. So it's going to be a little bit annoying to type because I tried it myself and it's a little annoying to make a fraction and whatnot, but use some parentheses and so forth, and you'll get there. And this little piece right here where, the limit piece right here, it's in the actual like menu down below the window box to type stuff in. So you'll see it. It might take a minute to figure it out, but it'll be okay. All right. So let's do another example here. So this one's a little bit harder. So same thing. I'm going to use a limit definition of a derivative, and here's my f of x. My f of x is 3x squared plus 5. All right, so there's f of x, and remember I also need f of x plus h. So I have 3x plus h squared plus 5. So I'm going to work that out a little bit more because I don't want to do that in my problem. It makes it's some more annoying. So I have 3. If I square x plus h, I get x squared plus 2xh plus h squared plus 5. So what I get is 3x squared plus, 6xh plus 3h squared plus 5. All right, so here's my limit. My limit as h goes to 0. And let me put that in there, f of x plus h. So it would be my 3x squared plus 6xh plus 3h squared plus 5 minus f of x. So it turns into minus 3x squared minus 5 all over h. All right, so time for some canceling. 3x squareds go away, 5s go away, and that's it. All right, so now I have the limit as h goes to 0 of 6xh plus 3h squared all over h. Now, I need the h in the denominator to go away as well, but I didn't want to do it earlier to confuse you. So do you notice here everything has an h? So I'm going to cancel this h with one of those and with this one. So what I'm left with is the limit as h goes to 0 of 6x plus 3h. So that's that whole expression. Now remember, if it's okay, if it doesn't break any rules, I'm allowed to just plug 0 in for h and go about my business. So when I do that, this part, 3 times 0 is 0, and so I get 6x plus 0, so I just get 6x. And so that is doing the derivative by the limit definition. All right, so now these next few examples are going to be quick because we're going to stop using the limit definition, but the first couple of problems on MathSpace do make you do that. So here, in this next example, I just want to write some problems for you. I'm going to see if you can discover the rule because there is like a quick little rule trick to doing this. So I'm going to make a chart. I got f of x, and over here is my f prime of x, my derivative. Okay. So I'm going to tell you that f of x is 5x. Now you know that that's a line. The slope of that line is 5. So my derivative is 5. So that one's easy. How about this one? F of x is 2. So you have the line y equals 2. So that one's kind of easy too, because you know that the slope of a horizontal line is 0. All right, so now here's where, start watching here. So f of x, let's say it's 4x squared plus 5x. So the derivative, without doing my limit definition, is 8x plus 5. So I want you to look at something here. I want you to look at like this and this, and this, and the exponent on the x is 1. So look at those two things as well. And then look over here at how I got this answer. All right, see if you can see what's happening a little bit. All right, so let me try one more. And then I'll tell you the rule. F of x is, 2x to the third minus 6x squared plus 4. So my derivative is going to be 6x squared minus 12x, and that's it. Now I want to go back and put some pieces on here. This 4 on the left, you could put an x on here, but put a 0 power. All right, so I want you to look at a few things. Look at this and this, and look at that and that. Then look at this and this, and look at this, and there's a 1 right here. All right, and then look here, 4 and 0, and everything went away. So let me tell you the rule. So the rule goes like this. You multiply your exponent with your coefficient, and then you take that exponent and drop it down a level. So you drop it to a 1. You multiply 1 times 5, and then drop the 1 down to 0, so that's why there's no x right here, and that's why this is a 5. So 3 times 2, drop the 3 down. 3 times 2 is 6. 2 times 6 is 12, and drop the 2 down to a 1. 0 times 4 is 0, so it's just gone, okay? But that's also like you have up here, when you have a constant, the derivative is always 0 because it is a flat line. All right, so let's do a couple more that get a little bit trickier, but not too bad. So if you had a function with a negative, like this, negative exponent plus 5x minus 1, same thing. Now, this, if you wanted to write this differently, it would be 3 over x squared. You don't know how to do the derivative of fractions yet, so you have to write it like this, all right? So let's multiply, let's use our rule. I have to do negative 2 times 3, and then drop the negative 2 down a level. So negative 3 times negative 2 is negative 6, and take 1 away from negative 2. When you have negative 2 minus 1, you get negative 3, so that's kind of different. This is 5x to the 1, so 1 times 5 is 5, and drop the x down a level, it would be x to the nothing, and then the negative 1 just goes away altogether. Because remember, it has an x to the 0, so it turns to 0. All right, so let's say we had f of x equals 6x to the 2/3 minus 4 radical x plus 5x squared minus 2. All right, so 6x to the 2/3. That's kind of weird, but whatever. So I'm just going to do 2/3 times 6. Well, 2/3 times 6, let's see, that's 12 over 3, that's 4. So I get 4 for my coefficient. And now for my new exponent, I have to take 2/3 and drop it down a level, so take away 1. So 2/3 minus 1 is negative 1/3. So this turns into negative 1/3. Now, the next part, this piece right here, that's really 4x to the 1/2, and there's a minus in front of it. So half of negative 4 is negative 2. And then if I take a half and drop it down a level, drop it down by 1, it becomes negative 1/2, right? And the last one, the 2, just goes away. Now, MathSpace is going to ask you to write this with positive exponents, so you could also write it like this: 4 over x to the 1/3 minus 2 over x to the 1/2. So if you ever get a negative exponent and you have to change it, just like this one, you could write negative 6 over x to the 3rd plus 5, because it wants you to write them with positive exponents. All right, so now it's time to give you the rule. So here is called power rule. So this is the rule for what we just did. So if you have a function and it's x to a power, all right, and it could be n could be any real number, I guess. All right, so what you do is f prime of x is n times x to the n minus 1. So you multiply n by the front, the constant in front, and then you take 1 away from the exponent. Another way to say it is this: d dx, which means the derivative of x to the n equals n times x to the n minus 1. This is just another way to express the fact that you want to do the derivative with respect to x of the item sitting right next to you. Okay. All right, so let's just do a quick few examples and we'll be done. I just got 3 more little examples. All right, so this next one, let's say I had to differentiate. To differentiate is a word that tells you to do the derivative. All right, so differentiate this function. Y equals, I got 4x to the 5th minus 2x squared plus 3 over 2x squared. So again, you don't know how to do there is a way to do the derivative of fractions, but this one you would always want to fix it because it would be very much easier if you would just make it into a non-fraction. So to do that, I have to simplify it. So remember, when you simplify, you basically do this. You divide these two, then you divide these two, then you divide these two, and you make it into one big 3-part expression. So let's do that. So 4 divided by 2 is 2, and then x to the 5th divided by x squared is x to the 3rd. Then in the middle, I have negative 2 over 2, so that's negative 1. And then x squared over x squared is just 1, so I'll just put a 1 right there. And then for the last part, 3 over 2, so that's just 3 over 2. And then my x has a negative 2 on it. So basically what we're doing is flattening the problem. So that way we're able to do the derivative. So my derivative is 6x squared. Remember, I'm multiplying this and then taking 1 away. The 1 goes away because it is a constant. And the last piece, I'm doing negative 2 times 3/2. So I would get negative 3 x to the I'm at -2. I have to take 1 away, so that would be -3. So if I had to write this properly, I would write 6x squared minus 3 over x to the third, which is how MathSpace wants you to write it. I mean, ultimately, it doesn't really matter. All right, a couple more examples, and then we're all done. Let me just add 2 more pages. I just got 2 more examples. All right, so let's say we had to differentiate this problem. Let's say I had 6x squared radical x minus 3x squared. Okay? All right, so again, the 3x squared is fine. This part right here, I have to fix this up a little bit. So that's 6x squared. Remember, square root of x means x to the 1/2. Again, there is a way to do the derivative of 2 expressions multiplied together, but you don't know that yet. So it's also easier in this type of problem. Let's just clean this up. Why don't we make this 6x to the, let's say, 2 plus 1/2. I can put those together. That's 2 1/2, which is 5/2 minus 3x squared. And now I can use my good old power rule. So y equals 6 times 5/2 would be 30 over 2, so that'd be 15. So I get 15 x to the, I have 5/2. I got to take 1 away. So that's 5/2 minus 2 over 2. So that's 3 over 2. All right. Minus 3 times 2 is 6, and I get x to the 1. So there we go. All right, and last example. Let's say I had this. Y equals x, 3x minus 1, and x minus 5. And you had to differentiate this. All right, so again, you don't know how to do something with products in it. There is something called the product rule, although you wouldn't really want to use it for this. It'd be better just to multiply this out because that would be the easier path. So let's multiply this out. I'm going to leave that x there. Let's FOIL this out. I get 3x squared minus 15x minus 1x, so minus 16x, and then plus 5. So ultimately, I have 3x to the third minus 16x squared plus 5x. So again, I haven't done my derivative. All I've done is basically fixed my problem so it looks better. All right, so let's do my derivative now. 3 times 3, I get 9x squared. Then 16 times 2, 32x, and then plus 5. And there you go. Now, sorry this video was a little bit long, but your homework for this after the first 2 or 3 problems will be super simple and shouldn't take you much time at all. And